Okay, guys, I think we can start today's session. And if you attended the last session, we have been discussing about ROS and Raspberry Pi, how to set up ROS on Raspberry Pi, and what are the things that we can do with that combination. So mostly like if you set up ROS on Raspberry Pi, you can run the basic stacks like navigation, manipulation stack like move it, then perception, everything in Raspberry Pi. I mean, based on the number of application that you are running. If you are only working with the navigation, it will be okay. So the importance is that we can run ROS in a small form factor. Okay, instead of putting a laptop, full-size laptop, or instead of putting an x86 machine, we can do everything inside the Raspberry Pi. So obviously there is a limitation in the Raspberry Pi computation, like the CPU clock speed and all. It is not very high, but it can run the basic features in ROS, basically the navigation, manipulation, and all. And also, like for the Raspberry Pi series, now there is an option to choose the RAM size, like 2 GB, 4 GB, and 8 GB. So I think if we are going with for 8 GB, it is I think it's more than enough, I guess. Okay, for working with an autonomous robot. And in the other side, for the Jetson series, only board that that is good for the hobbyist is the Jetson Nano. And if you're working with I mean products, and if it is if it is requiring a lot of computation, then you can opt for the Xavier or in Nano or something. Okay, so the advantage of Jetson is the CUDA. Okay, so I actually showed the advantage, like the CUDA cores actually. I mean, we can't compare the CUDA acceleration to Raspberry Pi, because Raspberry Pi, there is a GPU, but there is no GPU computing. There is not good GPU computing stack available for Raspberry Pi. But for NVIDIA, there is CUDA cores, and there is a good GPU acceleration stack available, so you can make use of it, mainly for the deep learning application. Okay, so these are the things that we have discussed last class, and today I want to jump into a new topic, that is move it. Okay, ROS move it. So I'm not sure you have worked with the ROS move it before, or heard about ROS move it before. So basically, it's an important package or a set of package that you should know. Like if you take the list of robots, mostly like I mean, you can find wheeled robots, that is one category, and there are manipulators like I shared in the last video. I think you have seen it, right? This category is the manipulators or robotic arms. So I had an opportunity to provide a hands-on training for this robot. Actually, this robot is called Kinova Gen 3, and it's from the company is from Canada, and and it's too expensive, and the gripper is from another company called Robotic. Maybe I can simply show you that. So why I put that, because we are using the Move It stack in order to work with these kind of manipulators. Okay, first I can show you the robotic arm that I have played with, and the gripper, 2-jaw gripper. Yes, so this is a robotic arm that I have shared, and it's a 6-DOF. It was a 6-DOF robotic arm, and I think there is a question. Yeah, so Tejas, this was not in ROS 2 actually. The driver was basically ROS Nautic, ROS 1. So they don't have the ROS 2 driver yet. I think they are developing it. So basically, this demo, no, this demo, uh, actually, I have to deliver this robot in NIT Calicut. That was the demo uh, purpose, and I need to provide a ROS training. So that was the intention, and I had an opportunity to like work on these robots. It's very expensive, like 35 to 40 lakh for both of these modules. So you can imagine. Anyway, like we are not going to buy, but for research application, a lot of people are buying it, and it's very accurate. So that's what the point that I need to emphasize is very accurate, very smooth. It's actually showing the quality of that 35 lakh Indian rupees. I mean, uh, because of the export, uh, it's not a export because of the import duty and all. It is slightly high compared to the um, actual price, but still, I will say it's very smooth. So that's what I got, and you can see you can work with rows, gazebo, the simulation that I will show you today, and move it. You can see here, right? Move it interface, and there is a MATLAB interface, C++, Python interface. I mean, it is having a good programming interface. They are providing it. So yeah, so this is a series of robots, that is the robot manipulators, and you may be also seeing these universal robots in some videos. I mean, I'm just showing some popular robots. Okay, so this is again a popular robotic arm which is using in the industry, mainly collaborative. I mean, it can be used for the collaborative robots, as a collaborative robot, and also it is, I mean, expensive as well. Okay, yes. So so in order to work with the autonomous robots, we have the navigation stack. In order to work with the manipulators, ROS actually having the move it. Okay, so maybe we can first see what is move it, and then we can see some demos and all. Okay, so basically, if you work with the robotic arm, so robotic arm is a series of joints, right? Series of joints, and in the joints there will be actuators, right? So all these actuators are connected, and then when we move one actuator, the tip of the robotic arm will be changing. So the importance is actually to the tip of the position of the tip. So you can compare with the our hand. Actually, we are grasping, we are manipulating things using our hand, right? So similar to that, if you want to do these kind of application using a robot, then we have the robotic arm. So just a second, controlling the robotic arm is actually a very tedious task, I will say. Maybe I can just show you robotic arm kinematics. So I just want to I'm not planning to explain kinematics or something. I just want to show you the complexity uh, in working with a robotic arm. So here, what you can see is a robotic arm which is having a set of links and joint. Okay, so any robots, if you take, you can find these links and joints, right? So in the robotic arm, you can see series of links are connected through joints, and each joint is an actuator. So yeah, so a series of joints, right? So the objective is that there is a gripper, or there is a hand at the tip of the robotic arm, right? I think you can able to see the link 7. It's actually a two jaw gripper, or like a gripper which is having two side basically. Okay, so the objective of this robotic arm is to take object using that gripper. Okay, that is objective, and like take pick and place, like taking one object from one side and putting it somewhere. Okay, so in order to do this application, just imagine how to do this. I mean, if a human is doing this task, you may be thinking it's a very easy task, right? But if you want to do this task with a robot, it's not easy, because the robot has to move to the object. Okay, sometime it has to identify the object and just move towards the object and pick the object. Then it has to go to another position and place the object. Okay, so what is the complexity? The complexity is that in order to reach the gripper of the robot to a predefined location, or like some location, for say a goal position. Okay, currently you can imagine the gripper is in a home position, or in a current position, or like, yeah, home, or like the current position. So in order to move the robot from current position to a goal position, I mean, how can we move the robot gripper to a goal position? Like, in order to move the robot to a goal position, each joints of the robot have to change, right? Like, then only this gripper will reach the goal position. So how to compute that angles? That is the complexity. Like, if I am giving the goal position of the robot, okay, of the gripper specifically, then how the robot computes its joint angles? Just think in our hand perspective. For example, we are putting our hand in a position in 3D space. Okay, then our brain is automatically adjusting the angles, right? So basically we are not caring about the angles that we are adjusting. But in case of robot, we have to care, because the robot is not intelligent. Our programs, like the programs that we are writing, is what the intelligent stuff. So that's what that is one component in MoveIt. Yeah, as Tejas mentioned in the comment, it is having some inverse kinematics implementation. So kinematics is basically the study of motion. Okay, study of motion. Basically, we are not taking care of the force and torque. If we are considering the force and torque acceleration, that is called the dynamics. Okay, so if you consider the motion of the robotic arm, there are two types of kinematics: forward kinematics and inverse kinematics. Forward kinematics is simply like, if you give a set of joint position, okay, then you can compute the gripper position. Okay, like you are giving the joint position to the robot, and then you can compute the gripper position. The inverse kinematics is, we are giving the gripper position, and the inverse kinematics algorithm will compute the joint position. That is what we require mostly. Okay, if you just give the goal position of the robotic gripper, then the robot joint angle should be adjusted in order to reach to that position. Okay, so MoveIt is having inverse kinematic solvers. Okay, and not only that, it is having a lot of features. I mentioned, right, it is actually a set of packages. It's not a single package, or it's not a single software. It is having a series of packages to solve, like inverse kinematics, then manipulation, motion planning. Like the inverse kinematics can be used to find the joint angles, but if you want to plan the robot motion, for example, if the robot gripper want to move in a zigzag manner, then we have to plan the trajectory, right? Plan its path, right? Plan the path of the gripper. So that is motion planning. Then control control in the sense, after the motion planning, after solving the inverse kinematics, we will get the joint angles, right? Then how to send that joint angles to each joint. So there should be some PID loops in between in each joint. Like, we can't directly set the joint angles in the robotic arm, because like if you just set a joint angles to 90, imagine the current position of a joint is 0, and if you are setting the position as 90, okay, without any controller, okay, it will quickly go to the go to 90 degree without any control. So that speed actually, that speed can damage the joints, because there is no control in between. But in a PID loop, what happening is that based on the error, the acceleration and deceleration will be, the speed is actually adjusting. Like, if the speed of movement is not all the same, while when it's starting, it may be like starting smoothly, then it will be accelerating, then it will be decelerating. But in case of a non-controller joint, there is no controller in between, so it will be directly setting the joint value, and it can damage the robot. Okay, so the move it is actually having controllers, and so these controllers can execute the trajectory in the robot. Okay, so it can send to these joint trajectory, can send to the hardware, maybe using a controller, so it will be very smooth motion. We can achieve very smooth motion. And also it is having the capability to work with the 3D perception. This is another important part. So I think you are familiar with the point cloud, right? We discussed with the PCL library, and you are familiar with depth cameras and point clouds. Okay, so the PCL is having an interface. PCL can be fetched from the depth sensor, right? And these depth sensors data, these point cloud data can be connected to move it for 3D object detection and 3D perception in general. Like, I can say an application. If you want to create an application like 3D bin picking, maybe I can show you that bin picking robot. Yeah, so like there is a bin in front of the robot, and it's not very structured. Like, it's simply cluttered, right? It's simply cluttered, and it's very difficult to take this object from this bin, because for human it may be very easy. Like, we can take it and we can classify based on the structure, but for robot it's a very, very difficult task, because in order to take an object from this cluttered bin, there should be some vision assistance. Okay, so there should be some cameras that is helping the robot to identify the object in 3D. Okay, so then only the robot can go there and take that object. Okay, so this is what happening in the 3D perception, because if you want to implement this kind of complicated task, we should require 3D perception. Okay, so move it is having an interface to 3D perception. Just connect the 3D camera to the robot, and then you can fetch the PCL data, and PCL data can be connected to the move it. Okay, then there is a collision checking, which is very important. So if you work with any robot, even if it is costlier or even if it is cheap, actually the collision checking, like self collision and collision with the environment. Okay, it's very important to do. Like, imagine um, a robot is self colliding, or imagine if it is colliding with the environment, the end result will be the robot will be damaged for sure, right? So if you see industrial robots, maybe I can show you that industrial um, robots. Let me take, yeah, so I think you may have seen this kind of pictures or videos, like, so why the robot is in the cage? Why we keeping the robot in a cage? The reason is the collision. Like, it's for safety actually, because the robot is actually placed in a workspace. Okay, workspace is the area that the robot can able to reach its gripper properly. Okay, so inside this cage or inside this workspace, robot can reach almost all the space, but outside this, robot can't. Okay, and also in this kind of robot there is no collision checking. I mean, if the robot is hitting a man, if hitting a human for example, it can't detect the collision actually. Okay, we can detect the collision maybe using some cameras or something, but by default there is no provision to detect. So if there is a collision with some human inside the cage, then we need to immediately press the e-stop button, emergency stop button. Otherwise, even some fatalities can happen. Okay, so for each and every robot there is some safety consideration for avoiding the self collision and also the collision with the environment. So the MoveIt actually providing some based collision checking. Software based collision checking, like you can add virtual obstacle uh, around the robot workspace, so the robot will not move to that obstacle. Okay, you can add meshes, or even you can use the point cloud data for the collision. Okay, so these things are very very important. So I think MoveIt is providing almost all the features that a manipulation application require. Okay, we can plan motion. Okay, we can plan the grasping in the sense like, in order to take an object from a table for example, we don't care, right? We can take an object in any pose. Okay, we are like automatically adapting into it. But for robot, it has to generate a trajectory, I mean a set of grasp poses, like in which pose the robot has to take the object. Okay, so it has to generate that, and then only it will find the better pose, and it will grasp it based on the best grasp generation available. Okay, so it is providing good grasping, then inverse kinematics, then control, 3D perception, and collision checking. Okay, these are some of the highlights of the movie. And the main companies are using it: NASA, Google, Microsoft, Fetch, Franga, Samsung. I mean, this is not limited. Okay, I mean, lot of people are using um, uh, MoveIt. Okay, and another advantage of working with MoveIt is, what basically MoveIt does is that you can plan the robot from A to B. Okay, in navigation stack, we are like planning the robot from A to B. For it is mainly for the mobile robots, or like wheeled robots. But for a manipulator, for a robotic arm, we can do the same like A to B planning using the MoveIt. Okay, and it also provide an interactive visualizer plugin. Okay, I will show you a demo, then you will understand. Also, you can work on the gazebo simulation. I will show you a demo of that. So you don't need the actual arm. Okay, I have shown you the costliest robotic arm that I have worked, right? 35 lakh, right? But if you want to work with that robotic arm, you can work it for free using a gazebo simulation. You don't need to spend any money. You can simply download the gazebo simulation, and you can create the similar application, not similar, the exact application that we are doing in the original arm in the simulation. Okay, and both will work. I mean, if you create an application using simulator, it will work on the actual hardware as well. Okay, so like that, there are many features. And why we are including Move It is available for ROS 1 and ROS 2, so there is no difference. The tools are the same, and for ROS 2 it is Move It 2. Okay, ROS 1 it is just the Move It, and for the latest version of ROS 2 also it is compatible. Okay, it can work with 22.04. So that is a thing, like this is the this repository, or this stack, this Move It stack is actively maintained by a company called Picnic. So you can find the yeah this is a Move It 2. Okay, so that's how active it is. Okay, this repository, I mean, the Move It repository is very active. There is an active community around Move It. Okay, so yeah, and there is a good documentation available. Okay, so before starting explaining the theory part, I think it will be better to start with the demo. Okay, so you will get an idea. Okay, yes. Okay, so let me start with the demo, and then I will explain the things later. So I am using a repository of Kinova called Kinova ROS. Okay, just a second. So there is a repository called ROS Cortex. Okay, and maybe I can share this link. So the ROS Cortex repository is actually the repository for working with Kinova Gen 3 robotic arm. Okay, so the instruction for setting this repository is given here. It's simply like copy pasting these commands. Basically, the intention of the Kinova simulation is we can able to work with the Kinova robotic application without the actual hardware. Okay, so the application that we are creating using the hardware and the simulation will be the same. Okay, that's actually a big plus, right? Like, you can create the application without buying the hardware. Okay, so I actually set up this stack in my PC. Okay, this is Noitic Devel, so you can set this repository. I mean, just copy paste this command. Okay, you can find like, we are creating a workspace, Catkin workspace here, and we are cloning it. Okay, you can simply set this package in your computer, and these things are for the Cortex APIs. Okay, that is Cortex for Cortex API, but you require that command as well. Okay, you can simply copy paste line by line, and I can show you the simulation. So the simulation files are keeping inside the Cortex Gazebo package. There is a package called Cortex Gazebo. Inside that, there is a launch file called spawn Cortex robot, and you can able to see the gazebo and the Move It. Everything is just popping up. Just wait for a second. Okay, I'm adding the motion planning. Okay, and so this is just a demo. After that I will start explaining. So here is the simulation of the robot. Okay, only the robot, there is no gripper, but you can add gripper, okay, by mentioning a command line argument. You can add the gripper as well. Okay, and this is the visualized robotica. On the left side you can see the gazebo, which is a simulator. On the right side you can see the RVs, in which you can set the goal position of the robotic gripper. Okay, so there is a 6 DOF um, 6 DOF marker that you will get. So just set the goal position of the gripper. Okay, I have set the goal position here, and then I have to press the plan button, and you can see the robot is actually creating a path and reaching that goal position. Okay, so you can see it is only happening on the right side, right? It's only planning is happening, but the robot on the left is not moving. So in order to execute this plan on the gazebo, you have to press this execute button. So you can find the robot is moving on the left side. Okay, and also I can just set the goal position, and then I can do both planning and execute together. So you can see it is planning and executing. Okay, so it's actually a basic function like moving from A to B, but it requires a lot of effort to reach. I mean, in the background there are a lot of computation happening to go from A to B. Okay, okay, so that's a thing. And I can also add the end effector, so you can able to visualize the robot with the end effector. So I'm just taking the cortex gazebo, and you have to just give the gripper that we are going to use. So along with the launch file, I just need to mention which gripper that we are going to use, and I'm using RobotiQ2F 140. Okay, just mention that. And if you want to add any other things like robotic arm gen 3, okay, that's it. Okay, let's start with the gripper, and just wait for some time. Okay, yes. Okay, so this was not the gripper that I planned. I think I have planned 85. This is 140. Anyway, just a second. Motion planning. Yes, you can find the robot with the gripper, okay, on the planning scene. And I can just move the robot and do the planning, and I can do the execute. So you can see the robot is moving to the goal position. Okay, and if you want to move the gripper, so there is a thing called planning group in Move It. So planning group means the list of joints and links that is participating in the in the motion planning. For example, if you select planning group as arm, then only the arm links, the main arm links are participating in the motion planning or in for doing the IK. Okay, the gripper is not at all doing anything. But if you change the planning group to gripper, and then the gripper is then selected, okay, and now if I'm setting the goal position of the gripper to closed, you can see the goal position is set, and then do the plan and execute, and you can see the gripper is closed in the simulation. Okay, if I set to open, you can see it is open. Okay, so that is what the gripper is about. I mean, the gripper planning group. Okay, so if you just simply change, you can plan the gripper and also the robotic arm. Okay, so I think you got an idea like regarding the capability. I mean, some of the capability of the ROS Move It. Other capabilities are like 3D perception, all these things. We need a depth camera, but Kinova didn't incorporate a depth camera on the on the end effector. So yeah, I think they will add soon. Okay, so this is one demo for the ROS Move It. Okay, so if you have any doubts, you can ask me. After this, we can discuss the concepts like the architecture of Move It, then the APIs, how to program the robotic arm using Move It API. So here we are programming or we are interacting with the robot using an end effect. I mean the plugin, right? The RVS plugin. There is a plugin called Motion Planning plugin, which is installing when we install ROS Move It on your computer. Okay, and but if you need to incorporate this planning in a program, then we need to we need to use Move It APIs, which can able to control the robotic arm. Okay, yes. And by the way, if you want to get the installation instruction of Move It, it's very easy. Like here there is instruction for Move It 1 and Move It 2. Just click Move It 1 and then look for the instruction. So it's very easy. Just copy paste this command and it will install. So it will support 18.04, 16.04, Windows 10. It will work, and if you need to install the Docker, that is also available. Okay, so I think there is a question. Just a second. Yeah, so in the simulation you can see or in the actual robot there is a camera here, right? There is a camera. Yeah, it's actually an Intel RealSense camera. Okay, but it's not the camera, I mean the actual camera that we are buying from the market. Is actually a customized version. Okay, customized version. Maybe you can see the robot image. Just a second. Yeah, see, this is the camera. Okay, so it's not the I mean it will not uh, it will not look like the actual Intel RealSense, but this is a customized version in the sense internally it is RealSense, but externally it will not looks like RealSense. Okay, and also the interfacing is different, so that's what I am appreciating this company, because they actually done the software in a very good way, I will say, because it's very easy to develop application, and it's very easy to get the images from the camera. So it's very they written the code in a very flexible way. Okay, and it's very easy to work with the robotic arm as well. Okay, so these are the I mean sensors available, and we have the robotic gripper. So you can connect any kind of gripper to this robotic arm. I think these I mean robotic cue gripper is actually compatible. I mean like a plug and play. Okay. Yes. So that is the essence of move it, like planning from A to B, and the robot will move to that goal position. Okay. So now I think it's a time to discuss the internal aspect. Okay. Internal aspect of move it.
Sorry, I have a
Yeah, yeah,
question.
go on.
Uh, can we use this same application for drones?
No, no.
Okay.
For drones, because it's actually require a list of joints and links. A series of, I mean, if you check a robotic arm, it's a series of joints and links, right? But for drones, I don't think so.
Means only stack. Move it is as you said.
Yeah, for
Okay.
move it is basically for wheeled.
Wheel-based,
Yes,
mobile-based, yeah,
exactly.
as you said, right? So then,
For drones,
okay,
actually, yeah,
mobility.
for drones, I think we need to use some other methods like there is localization and mapping for drones. It's a different algorithm for because for
Okay,
drones, no, the drones it doesn't have any encoders or like for getting the odometry, it can use the camera features to measure the position of the robot. So the algorithm that we are using in drones is pretty much different. Also the localization. It's mostly the cameras are using as a sensor to map in for mapping and localization. Yeah, yeah.
okay,
Okay.
okay. The reason for asking is you said mobility,
Yeah,
so
yeah.
I
So
just
there is a
was,
confusion. Like if we are
yeah,
using mobile robot, for example, if we have a word
okay,
mobile, yeah.
mobile
So
robot, okay, okay,
even
okay,
even
okay.
the robotic arm is a mobile robot. Mobile robot means it can move, right? But it is the
Yes,
base
yes,
is
yeah,
actually static. So then after that,
okay,
I specified wheeled robot. Yeah.
yes,
So
yes,
that
correct.
is what. Yeah, yeah. I got it. Yeah.
Mm-hmm. Okay, yeah.
Okay, so now we are going to see the architecture. What is inside this movie? Okay, how it is working. So that is what we are going to see. So currently, the documentation on the bottom, you can see the version of ROS that we are using. So currently, it's ROS to Humble. So in order to jump into Noitic, you can press here, and then it will switch into Noitic tutorials. Okay. Okay, so this website, it's mainly for ROS 1, Move It 1, which is a good resource for learning Move It. Okay, so they actually explaining the concepts using some good examples. Okay, so this is one way of learning Move It, and most of the important topics is referred here. And if you want to like create a perception pipeline, pick and place, grasping, all the things are documented. Okay, and selecting the IK solver for your robot, all the things are mentioned here. Okay, but we are going to see the architecture which is not in this tutorial page. Just a second, it's in the main website itself. So this is the reference, guys. This is the reference. Just a second. Okay, so Tejas is having a question. As you gave example of bin picking, is it possible to add the bin and cluster of items? Uh, yeah, so Tejas, actually what happening is that I mentioned that there is a 3D perception, right? So we can do the bin picking in different ways. One is that we can can create a cluttered scene uh, in RVs. That is actually possible, but that will be, I mean, that is not the actual way of doing for bin picking. Bin picking is mostly dynamic. Like we have a bin and we will, I mean, fill it with some, random stuff, and robot has to classify it. Classification is the main task in bin picking. Okay, so mostly it is doing through the 3D perception. So there will be a top camera or a camera on the end effector, and the robot has to detect each object and then classify it. So maybe I can show you. Let me see if there is any video. Yeah, let me see. Or just the bin picking. Yeah, I think there is another. Yeah, here from Fanuc, I think you can see there is a 3D laser or vision sensor on the top of this bin, and the robot is actually taking instructions from the computer, and that is connected to the camera. Okay, so this is the industrial setup. You can, yeah, there are a lot of videos. Yeah, just a second. Maybe I can show you another. Uh, Bin picking. I have seen an interesting video. Yeah, this one. Yeah, this is actually a demonstration of Pickit 3D. It may be a 3D robot solution. Okay, okay. Let me see. Yeah, so Tejas is having a question like for collision avoidance, it should be part of the same scene. Yeah, so Tejas, actually, uh, this 3D point cloud, no? This 3D point cloud can be used for putting the objects in the same scene. Okay, so maybe I can show you another video so you will get a clarity, because this 3D point cloud can be used to create a octomap. Okay, and then from that, or from the point cloud itself, we can run some 3D object detection pipeline, and then uh, we can identify the object XYZ position, and then send the robot to to that location. So it's not very easy, but you can find some solution. So this is actually a solution of a 3D robot, a 3D object detection solution. There is a company called Pickit. So this is the camera, it seems, and from the camera they are like identifying the objects, and they are marking the 3D XYZ, and the robot is taking each object one by one. Okay, so yeah, so this is the application that I mentioned. Okay, so it should be in the same scene. Like maybe I can move it 3D perception. You can see it is actually showing in the same scene. Yeah, this is one good example. Yeah, so this is a humanoid, and you can see there is yeah, so this is the input from the depth cam. Okay, depth cam, I think it's on the head. Okay, and these 3D point cloud can be converted into a representation called octomap, which is mainly using for obstacle detection. So you can see. So now the robot will not collide with these scene. Okay, it will always plan and it will always avoid this obstacle in the environment. So this is like a collision check with the environment from the from the output of the camera. Like camera is outputting the point cloud, and from the point cloud they are creating the octomap, and the robot is planning its path, uh, uh, avoiding this octomap. Okay, so that is one thing uh, that we can do with the 3D pipeline. I think I think one of the robotic arm is moving. It seems. Let me. Yeah. So that is how it is avoiding the collision. Okay. Tejas, I think. Yeah. Okay. Yes. So that is the 3D perception. Okay. Now let me move into their website, and here in the official Movit website, maybe I can share the link. This is a website. You can go to the concepts. Okay, so the first one is the tutorial, second one is the application. So in the application you can able to see multiple robotic application using Movit. This is very interesting, and all this application actually done using Movit. Okay, very interesting. Okay, so you can find many examples. The concept is what we require. Okay, concept is what we require, and you can see the system architecture here. It's not complicated. I am just comparing with the navigation stack, and you will get the things very easily. Okay, let me take the architecture of navigation stack as well. Okay, yeah, this is one diagram. Okay, and yeah, so let me put the Movit here, and let me put the navigation stack on the right side. Okay, I hope you are a little bit familiar with the navigation stack. There is a main node called MoveBase. Okay, and MoveBase is a main node which is having some plugins. Okay, like this MoveBase can load multiple plugins into it. So like global cost map, local cost map, local planner, global planner, all these plugins can load it. And then the MoveBase is having some topics which is subscribing and publishing. Okay, so we already seen the navigation stack many times, and if you check the Movit, it's almost similar. Actually, instead of the move base, we have a node called move group. Okay, move group, and move group is actually very similar to the move base. It's a single node in which we can load all these things as plugins. Okay, so for a robotic arm, uh, in order to do a to B movement, what we require is, one is obviously some kind of planner. Okay, some planner, and then IK solvers, then collision detections, and the planning scene, right? The planning scene is actually created from the 3D map. Okay, 3D point cloud, or you can create virtual obstacles as well in the planning scene. Planning scenes mean the environment around the robot, okay, which is contributing or which is participating in the motion planning. So on the right side you can see the planning interface, planning pipeline. So in the planning pipeline you can see the motion planners. Motion planners is responsible for A to B movement, and IK and all these things coming on the motion planner and collision detection part. And on the planning scene here, we can connect your depth camera into the robot motion planning scene. Okay, so that we can take the objects from the planning scene. We can avoid the obstacle, all these things that we can do. Okay, so after motion planning, what is the end result? I mean, the robot should move, right? After planning, we have to execute the plan, right? I think when you see the demo, you have seen two buttons, plan and execute, right? So let me show you that again. Just a second. Yeah, so here the robot is ready, and in RVs we have to set the fixed frame as base link, and then we have to add the motion planning. And now uh, we can able to see the robot here, and there are two buttons. One is for the plan, so I'm setting a goal position here, just doing the plan. But just doing the plan is not moving the robot, okay, in gazebo or in the real robot. We have to press the execute button. Okay, so then only it will be moving the real robot or a simulator robot. So that is what we are seeing on the left side. Okay, so the move group, when we press the execute button, the move group will be sending this trajectory, okay, trajectory that is already planned, into the controllers. Okay, move it is actually providing the controllers, and the controllers are attached to each of the robot joints. Okay, so when you send the trajectory, the controllers will execute this trajectory one by one, and these controllers will send the joint values to each of the robot joint. Then the robot will move. Okay, so these things, I think you got a clarity, right? On the right side there is a planning interface, planning scene, collision detection, and on the left side bottom we can see the controllers. So what is in the top side? I mean top, we can see RV's plugin, move it commander, raw action. Okay, so basically that is the interaction, interaction units. Like what we are seeing here is the RV's plugin. Okay, like we can interact with the robotic arm using what? Using RV's interactive marker. Okay, so this is one way of giving the goal position using RV's plugin. The first method is the move it commander or move it C++ API. That is, like if you want to move the robot programmatically, for example, if you want to move the robot like moving the robot from here to here, okay, then here to here. I mean, if you want to execute some sequence like pick and place or something, then you should implement some program. Okay, you should write some nodes. Okay, you should write some nodes. So that is where the move it commander comes. Move it commander and move it C++. Okay, so if you simply search, you can find the tutorial for writing C++ program using move it APIs. Okay, move it actually provides set of APIs. Okay, maybe I think it may be in the official website. Let me check. Concepts, tutorial, source code and API. Not that. Yeah, move it core. Yeah, mainly in the tutorial we have the API documentation. So that is what we need to check. Just go to the Noitic and you can see the move group C++ interface and move group Python interface. Okay, so you can write Python programs as well as C++ program in order to command the robot to move in a set of waypoints. Okay, so that is a programmability that move it offered. Okay, you can set your desired position, and you can open the gripper. You can then close the gripper, then you can place the object in some position. Okay, all these things can be programmed. Okay, so that is what the move it API does. Okay, yes. So if you check the diagram again, I think you got an understanding, right? You can program the robot using move it C++ and move it commander, which is the Python module. We can interface the I mean, you can interact with the robot using ROS plugin, and also some raw action that is not we are preferred. So this is the architecture of move it. Okay, so if you know the uh, navigation stack, I think understanding move it will not be much complicated. Okay, yes. So yeah, coming back to the main website, just a second. Okay, the concept we have clicked, and yeah, this is another diagram. I think I can a detailed diagram. Okay, yeah. So here I mentioned, right, uh, the the main node which is in move it is called move group, and move group is actually subscribing to the point cloud topic, which is taking inside the planning scene, and the move group is communicating to the controllers. So whenever we plan the trajectory, and when we press the execute button, it will go to the controllers, and the move group basically takes the URDF file and SRDF and configuration. So basically, in order to move the robot from A to B, we need a robot model, right? Here you can see this is a URDF model. I hope you heard about the URDF. It's a universal robot description format, which is an XML file which is keeping the robot links and join relationship. Okay, so if you have the URDF model, then only you can apply the ROS move it. Okay, then only so I will explain how to create the ROS move it interface after this. Yeah, but uh, just understand, you require the URDF and also the SRDF, which is actually I will say like an XML file format, XML file which is having links uh, for links and joins for particular motion planning group, like we have seen arm and gripper planning group, right? So that planning group things are seeing in the SRDF. Okay, we will see how during the setup of move it config package, and there are some configuration files. The configuration file is having like information about which motion planner are we using, which IK solver are we using, which controllers are we using. Okay, so this is very important. Okay, so all this information is required for the move group. Okay, and on the left side you can see the move group node is receiving commands from what? Move group receive the commands from move groups interface C++, move it commander Python, and the ROS plugin. Okay, okay, so these are the main things inside the move it. Okay, the move group node. Okay, move group node is the thing, and yeah, and I think you don't need to consider this for now. Basically it is showing the planning scene monitor and all, but this graph and this one will be enough for understanding the move it. Okay, yes. So if you have any doubts, let me know. after this, I can show you how to set up the move it configuration for a robot. Okay, for a robot. So I can simply show you that for an existing robot or like whatever. Let me see. Um, yeah. So if you have any doubts, let me know regarding the system architecture and block diagram. If you have any confusion, let me know.
Can you walk through one kind of stack and just to show the high level of how this in programmatically
Uh, yeah, so that's what I
infecting?
am going to show. Like first, we will set up a move it package, okay, and then we will see some examples of move it C++ and Python. Okay, so yeah, so that's what we are going to see next. And any other confusion? Any other? Okay, so now I think we can go to the next tutorial, like how to set up, uh, how to configure the move it stack. Yeah,
This this race move it also be used in the
yeah,
robotic
yeah,
arm in
yeah.
surgeries.
Not in surgeries.
Yeah.
Like you can see the industrial robotic arm. All these are using move it, but the
Mhm.
thing is that it doesn't say like it is only using move it, but it is having the move it compatibility. That's what it is indicating.
Okay.
And some research, yeah.
Okay.
So most of the robotic arm is having their own interface and also move it interface. So yeah, if the researchers are using like these robotic arm now, they will be using move it. Okay, not their proprietary packages. Okay, so you can see which all are the robotic arms supporting by Moveit, and the good thing is that you can also find the repository, their package from, I think, uh, most of most of the packages they have mentioned. Just a second. Yeah, this is for Fanuc, I think. Yeah, yeah. Anyway, like we can jump into the next topic, like how to configure move it for a robot. Okay, robotica. So what are the prerequisites to create or interface a robotic arm to move it? So the first prerequisite is there should be a URDF file. Okay, there should be a URDF file which is the 3D model of the robot. Okay, so I'm showing very uh, quickly, like maybe I can explain it later, but this is maybe in the next class or something we are seeing the move it in detail, but maybe I can show you. So there is a thing called move it setup assistant. um, Demo, yeah, move it setup assistant, run, just a second, setup assistant. Okay, so there is a package called move it setup assistant, and inside that there is a launch file called setup underscore assistant. Okay, maybe I can, if you install move it on your system and if you execute this command, you will get a wizard actually. Okay, software wizard like this. So this is a wizard that we are using in order to make a robot compatible with the move it. Okay, so what is the first thing they are asking? They are asking like, do you want to create a new move it config package? So basically a move it config package will have the configuration files, srdf, and also the different configuration that we require to interact with the move it, and some launch files and all. Okay, so and also like if you want to interface to a real robot arm or a gazebo simulator, there is an option to do that. Okay, So first I'm just uh, showing you an existing movie configuration package. Okay, like if you click the edit existing movie configuration package, which will help you to modify some existing movie configuration package. So what I am trying to show you is that, so you will get an idea of from the existing. Just a second. Zen 3 2F 140. Yeah, from this I think it will be good. Okay, think there is some problems. Unable to locate. Just a second. Let me take it again. Let me see that is working. Otherwise, we can jump into new move it. Let me try Cortex move it. Okay, Gen 3. Okay, okay. Think there is some issues in editing. Maybe what we can do is we can try to create a new one. So let me try create new package, and what we have to do is we have to just show the URDF file. Okay, so I am trying to take the Kinova Gen 3 robotic arm. So the URDF of any robot in working in ROS, we are keeping like a package like a name underscore description. Okay, for Kinova it is showing like cortex underscore description. So just click it, and then we can see arms Gen 3 6 DOF URDF. So we can try with Gen 3 transmission. No, Gen 3 macro. Let me see. Okay, maybe I can try with Gen 3 macro. Let's see if that works. Okay, because yeah, just a second. Robots, yeah, let me try this. Yeah, this seems like working. Yeah. Okay, so maybe I can take it again. So what I did was I just selected a sacro file or URDF for creating a new movie config for that robot. So I'm just going to the workspace, Kinova, then the description, and the high level sacro files are in the robots folder. So you can find Gen 3 robotic Q, Gen 3 Lite, Gen 3. So I'm going with the Gen 3 robotic Q 2F85, and then load files, and then you can able to see the robotic arm that we have played. Okay, and you can also see the collision boxes. And then this is I mentioned, right, this is a wizard, so you can check like the self collision. If you want to check the self collision metrics, so there is a thing called self collision metrics, in which we can decide which collision we have to include for self collision and which links we have to ignore, because all this self collision and environmental collision will take some computation. Okay, so in order to optimize the computation, we have to select uh, the 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 links that is participating in the collision. I mean, participating in the sense it can happen, that collision can happen, so that we have to include in the metrics. Other things we have to disable it. Okay, and then there is a virtual joins, planning groups. So this is actually a wizard, and we have to like create something in the wizard, and then after that we have to generate it. So this is like an auto generated wizard. So if you configure the value here, okay, then this wizard will be creating a package, a ROS package, which is having all these configured parameters. Okay, so I'm just creating a new package, and in order to avoid this self collision, you can just click the generate collision metrics. So it will show which all are the joints are disabled automatically. Okay, so these kind of joints may not be participating in the collision, so all these things are disabled automatically, but we can enable it, okay, anytime. Yeah, so these are disabled. Okay, so we don't need to do anything. And then adding a virtual joint, this is like if you are putting the robot in a mobile robot, okay, this robotic arm in a mobile robot, then also we can interact that complete system with move it. So in that case we may need a virtual joint. Okay, so currently there is no mobile platform, so we are just leaving that. And now we have to create the planning groups. So I think you have observed that planning group, right? Arm and gripper. Okay, so arm means like if you press the add group, you can name it as arm, and then arm includes the main joints and links in the main robotic arm. Okay, robotic arm in the sense the robotic arm is only up to this. After that it's gripper, right? So we have to just select which is the kinematic solver that we are going to use for this robot. So there are list of kinematics plugins available. Kinematics plugins means inverse kinematics plugins, and you can select some existing or you can create your own kinematics plugin. So I'm just giving KDL kinematics for example, and then you can also select the motion planning planner. I mean, I'm just making as none default planner. So the important thing is like add kinematic chain. Okay, so the planning group called arm, it is actually starting from the base link to what? Base link to the end effector link or bracelet link. Yeah, so I think the robot arm is from the base link to the bracelet link. This is the end effector link, that is not actually the end effector link. Let me check whether it is a part of the robotic arm. I think no. Okay, so maybe we can for a test, I think we can set the base link of the robotic arm as base link, and we can add the tip link as the bracelet link. Okay, and then we can save it. So what we have done was we created a planning group which is starting from the base link to the bracelet. And also we need to add the next planning group called gripper, in which we can add the links. Okay, gripper, we can simply add the links. So for the gripper, camera is not included. This all actually part of the gripper. We can add to the link, and also we can add the joints. Let me check what are the joints. So this is like a automatic wizard. Like we can add what are the gripper joints available, so that also we can add to the right and save it. So this is like we have created two motion planning group, and then we can the next thing is like we can add poses. Like we can say home pose. okay, home, and you can make it as something like this, okay, and you can save it. So whenever we uh, we call the home position, it will go to this position, okay. Like that you can create any pose. And this is the end effector. uh, so here, yeah, you can simply give the end effector name as gripper, end effector group as gripper, and parent link is the I think it's a base link or the bracelet link, I think. Okay, then the passive joints, which are not uh, having any actuation, so currently we are just leaving it. And then controllers, like the controllers are connecting the robots to the actuators, I mean the move it planning scene, or the robot in the move it to the actual robot or the simulation. So you have to create the controllers. So there is an option to add the controllers automatically. As of now we can do like this. And if you want to create the simulation interface, you have to add the hardware interface things to the URDF. Okay, so that will be automatically generated. So you have to copy paste these things to the URDF. So just leave that now. And then if you want to connect some kind of depth sensors in form of point cloud, you can select it. As of now I'm not selecting it. And after that I can just give the other information and mail ID, and then finally we can generate the package. Okay, so if you press generate, it will be like saying like no virtual joints added. Maybe you can give like test move it. So this will be going to this folder. These much of configuration launch files are going to this package, and you can see the configuration package successfully. So I'm just roughly seeing this wizard. Um, yeah, so there is a question: point cloud versus depth map. So in the 3D perception, the point cloud is the 3D. I mean the 3D point cloud that we have seen, but depth is the image actually, depth image. Okay, so if you only have the depth image, then you can use that as well. Okay, so that is what the depth map. Okay, yes. Yes, so after configuring, just go to the home folder, and we can see the test move it folder, which is actually the package that we have created. Okay, so if you just move this package into any of the workspace, for example Catkin workspace, or like yeah, Catkin workspace, and if you build it, I'm just doing a Catkin make here. Catkin make. So essentially using this wizard, we are creating a ROS package, and then we are putting that package inside the ROS workspace, and then you can see some launch files in order to start the planning. Okay, so we can do the planning without simulation or without the actual hardware. We can execute in a fake controllers. So maybe I can show you that. I mean, this is an abstract. I think we can discuss in detail later. Just a second. Test package. So the package name is test move it. Okay, so just ROS CD, just move it. Okay, so the package is existing, and then just move it, and you can start the demo dot launch, so which will be showing the RVs for motion planning. So this package is not very optimized, but you can see yeah, the arm actually popped up, and you can do the simple motion planning, I will say. It's not very optimized, so if you do plan, you can see it is doing the planning, and it is also executing. Okay, so you may be thinking like where it is where the controller executing. So you can see here there is a fake execution. Okay, fake execution means if you don't have any simulator or the actual hardware for sending this trajectory, the MoveIt will be sending the trajectory to a fake controllers. Okay, so there is nothing happen, like it will be executing in a fake controllers, and yeah, that's it. Okay, so this is what the MoveIt config package is. Like the MoveIt config package is a ROS package which is having a set of configurations and set of launch files, and these things are automatically generated based on the inputs that we have given in the setup assistant wizard. Okay, so if you are giving correct values, like for the it asks for the kinematic solver, controllers, sensors, all these things. It actually asks, right? So all these configurations will be stored in the YAML file. Okay, so this is how we are creating the configuration file for MoveIt. Okay, so I think we can stop at this point. Okay, we can stop this at this point. Tomorrow we can continue with the programming part and also the wizard. I can show it in detail. Okay, yes, so let me know if you have any question. We can continue with MoveIt, and then maybe we can jump into the Nodlets if we get time. Nodlets and Gazebo plugin. I'm not going in an order, but yeah, let's see. So let me know if you have any questions regarding the basics of MoveIt. Do you have any question, guys? Like, I think you got an idea, right? Like, what is MoveIt and what is this MoveIt config package, right? If you have any confusion, let me know. Okay, I think it's okay for you. Okay, so today I think we can conclude up to this topic. There are some interesting yeah, there is some interesting yeah, things, like it is showing the animation like a trail. We can see the robot motion in 3D. Yeah, okay guys, so I think we can conclude for today's session, and tomorrow we will be continuing with MoveIt and examples, and also we can see the setup assistant initially. Okay, again, yes, so thank you guys, thanks for attending. See you tomorrow. If you have any doubts, yeah, you can
Uh,
post it. Yeah,